fine-tuning. It's actually a technical term in physics, and it does not necessarily imply design. It's simply a metaphor. So even though the metaphor does refer to a fine-tuner tweaking some knobs or doing some kind of precision engineering, within physics it rather refers to the predictions of a theory. If they're fine-tuned, then it's requiring a suspiciously precise parameter setting from within a range of possibilities. It has really nothing necessarily to do with design as used within physics. We're less confident in theories that are so flexible they can explain any observations, because in those cases you can just go back and tweak some parameters and it'll automatically fit the data. It doesn't give us confidence in a theory that makes very broad predictions but then relies on fine-tuning to match other constraints. For example, suppose a theory proposes a mathematical model involving, say, a dozen linear equations, and you have a dozen unknown constants. If your theory doesn't constrain the values of those constants within narrow ranges, if they could be anything, then literally that mathematical model could describe all possible observations, because you can always solve that set of linear equations for a set of constants, which would be consistent with any data. So there would be no really specific predictions whatsoever from such a theory, and therefore you wouldn't be able to confirm it. More broadly speaking, though, that's often you have a situation where you have predictions, and it's not quite as bad as that example, but you still have a situation where, by Bayes' theorem, the narrower your prediction is, and it gets satisfied, then the more that you find confirmation for that theory, as compared with a theory which predicts a broader value. So consider this example of two graphs here. So the x-axis here represents possible parameter values, and we have a black sort of box or rectangle there showing some constraints that limit the range of valid parameters based on some other criteria that's independent. And then we have a theory which makes predictions, shown in blue here. Theory 1 predicts something relatively narrow, and so when we find that the value that is consistent with that is as predicted, then that provides a decent amount of confirmation, as compared to theory 2, shown in red, which makes a much broader prediction. So on that theory, there were so many things that could have been consistent with it that we don't gain as much confidence that that theory is correct. So if the only criteria for evaluating the theory 1 and theory 2 here are these particular predictions, then we would have more confidence in theory 1 than theory 2, because theory 1 requires less fine-tuning. So let me give you an example, an analogy from outside of science that might make more sense if you're still struggling to track with this. And to do so, I can't think of a better analogy than what was in this book. This is called The Fortunate Universe by Geraint Lewis and Luke Barnes. I think it's the best fine-tuning book out there for the popular level, or maybe for any level, because they do get into a fair amount of detail on the science, and yet it's fairly accessible. It's a good overview of the science of fine-tuning, and what's especially interesting is they try to analyze, well, what is the best explanation of the fine-tuning? Luke Barnes, a theist, argues for God, a fine-tuner, as being the best explanation of the data, and Geraint Lewis, an atheist, argues for a multiverse explanation, where he argues that there may be these unseen universes out there, a plethora of them with different laws and constants, and we just happen to live in the one that permits life, and we can only find ourselves in one that permits life. So that's his explanation, and you can see the interaction. But the interesting thing is that they both agree on the physics, actually, other than one footnote. But yeah, they're very much in agreement that the universe is finely tuned for life, but then obviously there's a lot to unpack and evaluate to look at what would be the best explanation of that. So they give this example anyway. They speak of a situation where someone's robbing a bank and they enter a 12-digit code and they get it right on the first time. Okay, so you've got some kind of video surveillance, presumably, and you see this happen. What can you draw from that? Well, you get strong evidence then that this is an inside job. That theory is favored very much over the theory that they just got lucky. Okay, if they just got lucky, you can think of that theory as entailing a series of sub-theories. In one sub-theory, they enter the code 0000, etc., all zeros. Another sub-theory is the same thing, ending in 1, and so forth. You literally have a trillion sub-theories, but nothing within the chance just got lucky sub-theory prefers any one of those sub-theories over any other. It requires fine-tuning to explain the data that they actually entered the one right code. By contrast, if it was an inside job, they may have had that information ahead of time, and you would then have a more tidy explanation for why they chose the particular code that they did. So that's kind of an example that may be helpful. Another one, akin to fine-tuning from science, but I think still easier to grasp than some of the physics ones where you're talking about parameter space, and it can be a bit abstract for some people. Consider the theory of continental drift. In 1912, Alfred Wegener proposed that continents were once connected, and that this would explain certain features that were otherwise mere coincidences. So if you look at South America and Africa, for example, you see that they sort of fit together, and there's a similar shape to them. And then he noticed, he had information even at that time that showed that there were fossils that spanned the boundary of those continents and other ones, and that there were also mineral patterns that seemed to span continents of boundaries on the hypothesis that they were once together. And so this kind of data would not be explained well by the static continents theory, which on that theory, it's just sort of random where these bands were. There would be no reason to predict that the edge of one continent would have a band that connects to the edge of another continent. So it relied on a series of coincidences and required fine-tuning to explain the data. And by contrast, the theory of continental drift provided a natural explanation rather than one which relies on coincidences. So similarly, fine-tuning within fundamental physics occurs when a narrow range of parameter values satisfies some independent constraint, but the theory itself allows for a very broad range of possible values for that parameter. Check out our video on how fine-tuning applies to life, and we'll look at that next time.